Good morning. We'll wait for a couple of minutes and start the session. Good morning. Welcome to the second lab session. In today's lab session, we will be looking into different various classification models. In the last session, we went through uh, different various types of EDA, the different kinds of analysis. We checked on that, and then we went through logistic regression. So in this session, we will be focusing on one, how we manipulate data sets to create a new data set, one, and the classification models. The focus will be more on these two things rather than the EDA part. In case of any clarifications, you can always write to me or you can start a discussion thread to if you have any queries. Okay. So today's lab session, we will be looking into classification models. The case study which I have chosen for this particular uh, session is a loan prediction data set. Okay. In this, what we are trying to do is we are having the loan data set from which we predict whether the loan will be approved or not. Okay. So here the most um, major stages followed are as such: data acquisition, data preparation, exploratory data analysis, feature engineering, and model building. Yes, feature engineering is one more a step which we'll be going through today. In the last session, we focused more on the exploratory data analysis. So this time it will be about preparing the data, feature engineering, and model building. Okay, to start off, So basically we have a set of data. So what does the data contain? Data in this particular case has details like income of the applicant. We have this applicant name, age, ID, so on and so forth, job type, marital status, credit history, loan amount, tenure. So these are the kind of data which is collected. So in this particular case, what happens is the data is the customers are categorized in three different ways: urban, semi-urban, and rural. So we have at hand three different datas which contains customers from urban with the list of different features collected from them. Similarly for semi-urban and rural. Okay, these data sets are provided in three different CSV files. We need to acquire, and then what is required from our side? From our side, we need to first combine all these three, create a single data set. I am not building three different models for these three different categories. What is required is we combine, create a data set first, right? And from there, if the features are given, we are to predict whether the loan is approved or not. So for the focus will be on how to create an uniform data set wherein the data from all these three CSVs are represented. That will be the first stage. In the previous session, what we did, we had a clean curated data. All we did was upload the data set directly as a data frame and started implementing different techniques on it. Right? But whereas here, the first step is to combine these CSVs, combine all these data sets and create a single data set. Right? How do we go about it? Similarly, like the initial stages where we discuss, we import the required libraries in this particular notebook, in this project. The same core libraries apply: pandas, numpy, seaborn, and matplotlib. The first step, we import the required packages. Import pandas as PD, numpy as NP, seaborn as SNS, matplotlib as PLT. All right. So this being the first step of importing the required libraries. Usually what we do, the second step being loading the data set, wherein we say, right, df pd.read underscore CSV and give the dataset.csv, right? That would have uploaded the data. Now, what is happening here? We have three data sets. We have three. So those are urban underscore loans, semi-urban underscore loans, rural underscore loans. We have these three CSVs available with us. So what we do, we first read them, upload these three, name them as urban data, semi-urban data, and rural data. So we are creating three data frames. Read the data, find out what are in each data set. Find the data shape. Find the data shape, okay, of all these three. On doing that, what do we do? Now, when I'm looking at all these three data sets, I'll have some common features, right? And then what do? I try to correlate what is the common features in it, what names have been given, how do I combine it and make it as one single data set. I would name it as loan data. Okay, I have this urban, semi-urban and rural. Now I want to combine all these three and then make it as a loan data. So what is required is, now we have loaded all these three sheets, all these three data sets. Check the various columns. Some of them might look different or, spelled differently, but will be representing the same data. So what is done? We combine them. Okay. We make it as a common feature. So how do we go about it? So first, to check what are the different columns are available in this three data sets. So here we set urban underscore data dot columns dot append. So what this does is it appends all the columns from the different data sets, and then the list of columns is presented. When that is done, we can see that loan ID, LID seems to be the same. Co-applicant name, income, co-applicant income, it's with a underscore, without a space, right? So these are all same data, but the columns or the features are named differently in the different data sets. So what is it we do? Now, once we analyze the different features, I would suggest you finalize the feature name which has to be used. For example, in case if you are saying loan ID or LID, then you decide on loan ID. Then you retain the loan ID. And in all the three data sets, this loan ID it becomes common. The features values from this one will be stored from all these three data sets will be stored under the loan ID. Right? Similarly, for gender, sex, decide on what kind of, how you want to name the feature. Say gender, then all your gender information from three different data sets are stored under this name. That is what has been done. So finally, what happens? This set of, when I'm trying to merge, we have decided on loan ID, gender, married, tenure, education, self-employed, income, co-applicant income, credit history, dependence, loan amount, and approved. The approved would be the target. The entire business problem of this particular data set is to, when given a set of values, whether that particular customer loan will get approved or not, to predict whether they get approved or not. Right? So this is the data preparation. Then what happens once we uh, prepare the data, we go ahead with other steps, the processes of, EDA, feature engineering, and model building. Let's have a quick look at the notebook. We'll wait for a couple of minutes. Use your virtual labs for all your lab worksheets and as well as your assignments. Marks will be cut if you're not using your virtual labs. So start your virtual lab. We'll wait for it to launch. It generally takes a minute or so for the instance to activate. The data set and the notebook used in this demo, in this session, will be uploaded in the e-learning portal. Please download it. When you're watching this, please run the notebook simultaneously so that you get a hang of it. And please reach out in case of any clarifications required. So here we go. The virtual lab is being launched. We will be seeing on how we are combining all these three different data sets: the urban, the semi-rural, and semi-urban and the rural. Three different data sets are combined, merged to form one single loan data set. And that loan data set will be used for building the model. It will be a single model. It will not be three different models for, urban, semi-urban, and rural. It is launched. Let's start a Jupyter notebook. I have already updated the notebook here. I will be sharing the same with all of you. Please run the notebooks. See how it works. See the kind of syntax used. See the kind of inferences done. Like I said, in this notebook, focus is more on the data preparation, right? EDA, yes, we have done a set of EDA, and then the focus is on feature engineering. In this particular notebook, we have derived features. We have a set of features. We had three data sets, merged it into a single data set, right? And then from there, the final set of features, some extra features are derived which would help while, we are using our ML models. You will notice that the three different data sets here are given: the urban loans, semi-urban loans, and rural loans. Okay. This is an understanding. What we discussed in the PPT is what is been presented here in the notebook too. It'll be a good quick reference for all of you. Now, data acquisition, package import. We have imported only the core libraries required, the pandas, NumPy, Seaborn, and Matplotlib. As and when we require different libraries, they have been imported in the same cell. The initial stages, what we are doing is we are uploading the data and reading the data. For the first being the urban loans, we see here we have loan ID, gender, married, self-employed, education, so on and so forth. Similarly, semi-urban CSV has been updated, and we see here instead of loan ID, it is called as LID. The loan ID is shortened and it is referred as LID. Gender, applicant, the way the features are presented are also jumbled. Not that it matters. We will be able to, when we are merging, we'll see to it that the column which is required here, applicant income applicant income. Here it's in the second, third, this one, it's in the later stage. Will not matter because when we are merging it, they will be put in the right order. Similarly, if you see here in the rural data set, you'll see loan ID, sex, marital, dependent, self-employed, education, loan term, loan amount, income, still loan status, right? Here we see that some of the features are missing when compared to the other, other two, like the urban data set and the semi-urban data set, right? So what we are doing now, first we will see what are the different sizes of it. We see here in urban and semi-urban, it is 12 and 12, 12 columns and 12 columns. Whereas in rural data, it is just 10 columns. When we are merging the data sets, we will be looking into it on how to handle it, right? What kind of features are there? Can they be dropped? Or do we need to correlate them? How we going to handle it is what we will be seeing in the coming column cells. We'll having a quick look at the columns. What happens? Loan ID, gender, married, right? Self-employed, education, right? Applicant income, dependence, loan amount, tenure, co-applicant, credit history, approved. Now, this approved is being the um, target variable. Similarly, if you notice here, it is same. LID is loan ID, gender, applicant income, yes, we have, dependents we have, education we have, marital status, here it is as married, self-employed is again available, loan amount, loan amount term, and here it is named as tenure, right? Co-applicant income, again we have that, credit history and approved. So urban and semi-urban data is going to be a easy thing to merge because the way the features are named are slightly different. Otherwise, both the data sets have similar features and the equal number of features are also same, 12 and 12. Whereas coming to the rural data, what happens? Loan ID is given, gender, sex, okay. Marital status, okay, fine. Dependent count, okay. It says as dependent, self-employed, yes. Education, yes. Long term, yes. Loan amount, income, loan status. Loan status is our approved or not. So what is missing? Most common thing which is missing is the co-applicant income and the credit history, right? Loan term is can be mapped, all this. What are the two missing columns we see? It is the co-applicant income and the credit history are missing in the rural data. So here what we will be doing, how this is being the three raw data from three different data sets, and then we are going to structure it into a proper data sets, right? Here we are listing all the different columns names from all the data sets, from three different data sets, that is the urban, right? It is basically listing the column names or the feature names. So we saw this seems to be common. So we decide on the final column. So what are the columns we are retaining? Loan ID, gender, married, tenure, education, self-employed. 6, income, co-applicant, credit history, dependents. 10, loan amount and approved. So we are retaining 12 features. When we are finalizing the data, we are, the final data set, the loan data set, will have all these 12 features in it. So when we are going to merge, we need to see that it is in the same format. Like, when we having the naming of the features as it differs, it might. if you see, like the gender might have M and F, or male or female. All right. So we are finding for the categorical, this one, we find the unique values. Gender, married, self-employed, education, credit history, approved. Right. So we see that these are the unique values in the urban data set. These are the unique values in semi-urban data set. Right. And this will be the unique values in the rural data set. So now what we do is we standardize this values, right? We will standardize this values stating that for gender, I'm either going to use M and F, or I'm going to say male or female, right? So that's how it is. This is, you standardize the data, decide on the data. It is not that this is the right way, that is the only this particular way is the right way. No, as long as it is standardized across all the three data sets, then it is fine. So first, we start off with standardizing the data set. Sorry, the feature names. We come up with the feature names, we finalize them, and those are here mentioned. So this loan ID, gender, married, self-employed, education, applicant income, dependents, loan amount, tenure, co-applicants, credit history, and approved. These 12 are the finalized feature names in the loan data set. Now, what is it? One extra thing we have included here is property location as urban. So then we don't lose out on where the loan was applied. Correct? So here we have now 13 features, wherein one feature will refer to the property location, saying whether it is urban, semi-urban, or rural. So this is how it is standardized, and this is how it looks. Similarly, we do the same for semi-urban, right? We do it for the semi-urban and normal. Okay. Now here, when we have standard and decided that unique values are going to be such and such, that also is standardized in each and every data set. Okay. What I have done here is I expected it to be a interactive class wherein, an hands-on session, right? So I would have attached the files. Like I said, you will be getting the files. I mean, the files will be uploaded in the e-learning portal. What I would suggest is you download that, and now I want you all to go through the notebook is also shared. Please upload the notebook. Go through the steps till this point, wherein we have standardized the feature names. Okay, standardize the unique values, so that the unique values as varies a little from data set to data set, that is your urban, semi-urban, and rural. What we'll be doing is we are standardizing all those two. Okay, we'll take a 10-minute break here. I want all of you to go through those steps. Go through those steps. Understand them. Okay, I hope you don't have any queries in between. If so, mail it to me or start a discussion thread. I shall pause here for a couple of minutes for you all to check out the notebook. Like I said, when you're going through these steps, finally you arrive at the loan data, which has 114 rows and 13 features in it. 12 were the independent variables. 12 variables were features were present in the raw, whereas now when we are combining, we created a new feature called property location, wherein we have mentioned whether it is a urban, semi-urban or rural, right? So we have a data set of shape of 114 with 13 features. Check this out, then we'll start again in a couple of minutes. I hope none of you have any queries. If you have queries, please feel free to reach out to me. The next step would be the exploratory data analysis, right? Let's have a quick look at the notebook and then we shall continue. Share my screen. So here at the instance, it is locked. Use cloud password. Right? So here we saw that we standardized, right, the unique values, made it even across all the three data sets and created the final data set, right? So how does this look, right? We have standardized for each and every urban, semi-urban, rural. The steps remains the same. Then the final stage is where we merge it. Merged frames, right? We say we had initially when we loaded the data set, we had named it as urban DF, semi-urban DF, rural DF, right? Now, when we are defining the merged frames as containing all three, right? Here, what is done? The loan data, then we concatenate the all these three different data sets. right? So then what do we have? What happens? We make a copy, and here when we see these are the different columns which we decided on and standardized, right? And all of them, all these three, we standardize them, right? Including the extra feature of property location, right? So what happens? Now the loan data has concatenates all these three and creates one single data set called as loan data. If you see the head of it, you will see loan ID, gender, M&F is used, married, yes or no is used, self-employed, 0 or 1 is used, education, graduate, non-graduate, applicant income is a numerical, dependent again, loan amount, excuse me, tenure, okay, co-applicant incomes, credit history, whether they have a credit history or not. What happens here for rural? It will come as no. Rural didn't have credit history in it, right? It didn't have it as a feature. So what will happen for the rural, the credit history, all the this one will rows will have no. Property location, urban, semi-urban or rural, right? So finally, this being the data shape, 114 with 13 different features. In that 10, 12 independent variables and one target variable, the target variable being the approved. Now comes the EDA part. In EDA, what are we doing in EDA? Similar to what we checked out in the previous session, when we discussed elaborately about EDA, we talk about univariate analysis, bivariate analysis, right? Just setting up some colors. Then now we are exploring the target value, right? We see the approved and not approved. Y approved and N not approved. We first see whether how much of variation is there. We see that 64 records have the approved values in it and 50 with not approved. All right. Then we try to understand more about the categorical variables like gender, married, some self-employed, credit, right? What are we doing? We are doing count plots. Categorical variables. What will we do? We'll do the count plots, right? So this is how the count plots look like, right? Then we infer what is it we are seeing from here. You see that most married people have a better chance of getting the loan approved. Males have a much higher percentage chance of having the loan approved, right? So these are some of the details, categorical variables which are analyzed and inferences are given, right? After that, we understand more about the categorical variables like the dependence, education, and property location. Again, same count plots or histogram, right? Pull it on to just check how the visuals are, see what kind of samples you have, infer what can be, what you see in the visuals. Moving on to the numerical independent values like the applicant income, co-applicant income, and the loan amount. We plot the numerical. For the non-numerical, we plot a histogram, plot. We plot a box plot to see whether there are any outliers and so on and so forth. And in case, yes, and it has to be mitigated, what kind of mitigation is to be applied. Okay. We see that, in the box plot, it looks like there are lots of outliers in it, but are they actually outliers? No. It is more of the majority of the applicants' income were less than 10,000, right? So that higher range looks like outliers. So do they need to be mitigated? No. Right? So these kind of numerical variable, the different numerical variables are explored, are visualized to see if there are outliers present, what kind of spread they have is what we see. Okay. Looking at all this will be one part of the exploratory data EDA. We'll also look at that in the notebook. We are printing the different variables, numerical variables, exploring them. Okay, we look at the categorical and see here the categorical of approved female, male, approved or not. A bar chart or a cross tab is drawn, right, to compare. Okay, within the gender, the initial plot wherein we saw it has separate bars. This is a cross tab wherein it shows as a ratio. Okay, with the target variable, we are checking different for the different variables, right? Categorical variables, and after that, we start off with the bivariate analysis. Now, bivariate analysis. What do we do in bivariate analysis? We take up two different variables and see what the relationship is between them. Right? Correlation analysis, what we have done is we are looking at the heat map. This is how the heat map is. We see that applicant income and loan amount has high correlation comparatively. Right? So these are some of the inferences we look at from the heat map produced or the correlation analysis. So loan amount and income seems to be like highly related. Loan amount and co-applicant seems to be highly related. Income and employment status are related. So this we need to see what kind of relationship, how high the relationship is. Is one of the feature going to be redundant? If there a very high correlationship between these two features, so if it is going to be very high, then can one of the feature be removed as redundant so that the model becomes much more efficient when we are developing it, right? So this happens. From there, what we do is we are moving here in this one I'm showing the model building, but let's go back to the notebook wherein we will look at feature engineering part of it. Let's look at the feature engineering part. We'll have a quick run through on the EDA and unlock. So univariate analysis, what are we doing? The categorical values and the first will be the target approved or not approved, target value distribution we check into. Then we are looking into the categorical values. Here and we see gender, right? Married, self-employed, credit history, right? Then comes what? The education, dependence, property location, right? These are the univariate, that is every single feature, how the distribution is within the unique values among itself. And then comes the numerical univariate analysis of numerical variables, in wherein we have applicant income, right? Showing the histogram and then the box plot. So like I said, are these outliers or not are to be inferred from the data, not just the visual. Just because the visual is showing has some of them as outliers doesn't mean those values are going to be outliers, right? So here we infer whether or not it is outliers and how they are to be handled. Similarly, we check into applicant income by education loan, right? That is we have done as a box plot. You can try some other plots if visuals if you want to, right? Again, we see here co-applicant distribution and the co-applicant income, all right, how they look at. So these are some of the various univariate and bivariate analysis you go through. All right. Crosstab is drawn for here for the categorical values. Now comes the best part wherein we have say 12 plus 1 target value. Then we like move to the next step saying that what else can be done. This being the final thing of correlation heat map. Now comes the part wherein we talk about the feature engineering. The initial feature engineering, what were the thing? We'll be handling the missing values. Then you check for any duplicates, right? Now we see that there are some missing values, right? Then we are using mean or median imputation for the numerical and mode imputation for the categorical. So here all the missing values are filled. Recheck, we see that there is no missing value. So this being the first step. You load the data, you want to check, right? Fine. Then coming to outliers. Okay. We see that, the applicant income distribution is very right skewed. So what is it we are doing? We are going to log transform so that the distribution is much more even, right? So this is one of the feature engineering which we are doing. So here the applicant income is now stored as a log. So a new feature value is created here, calling that applicant income log. So these values, log transformed values, are stored in this particular feature. Okay. Looking at the next thing. So this is how the transform after the log transform it looks like, right? When you look at the data now, when you look at the data now, so this is how it looks like, wherein you had 12 plus 1, right? And now what do you have? You have two different, this one wherein the log amount and the applicant income amount have stored as log values, right? The loan amount and co-applicant income. Sorry, applicant income, right? Applicant income and loan amount. These are now stored as, these are two features are added in the loan data set, right? Next comes the data type we have checked, and there are some which are, object and the integer values are mixed. So those are put right. Right. So here, when we are saying gender, the is category, married is category, all that is redefined to see that the data types and the columns, they match. Next comes the feature creation. In feature creation, what are the possible things which we can do? Here, there are two columns stating one has applicant income, the other has co-applicant income. So here we can combine these two, make it as a single column as total income, right? We can make it as total income. And then when required, we can just use that column and drop the applicant and the co-applicant income. This is the reason we create features, new features. One might give a different show a pattern, or couple of features can be combined and made as a single feature. Thus, what happens? The number of features fed into the model goes down, right? So that also can be done. Here, what happens? Now I am combining the applicant and the co-applicant to find the total income, right? So comes here, we create a data, we create a feature. called total income. When we see the distribution, we see that it is right skewed, right? So we are log transformation to make the distribution normal. Just what we did for applicant income and the loan amount. Similarly, we are applying log transformation to the total income too, right? Now, what are the other features which we can derive? Now, if we say that, okay, if I am approving a loan, then, the loan is returned in such and such tenure. So the EMI would be, will we be able to calculate the EMI? What is EMI? Off the cuff. This is going to be a rough calculation. It is not an exact thing. Yes, in a larger banking, this one, you have an entire different way of looking at how the interests are added and how the EMIs are arrived at. But here, to keep it simple, all we are saying is loan amount by tenure. Whatever the loan amount, we are not even thinking of the interest here. Just a thumb rule of just seeing whether the applicant will be able to do the EMI or not. So what I'm saying is we create one more derived feature called the EMI, which is obtained from loan amount dividing the loan amount by the tenure. So what happens again when we see this, right? Log transform, right skewed, log transform, right? Of the EMI, right? Compute balance income. So what is balance income? Total income minus your EMI. Okay. So what basically we are doing is we are trying to derive some features from the existing features in the data set, which would help us in building a better model, right? So balance income, we created total income, we checked EMI, then we checked balance income, right? All these are derived columns. So now what happens? This is the available features in the data set. Loan, gender, married, self-employed, education, applicant income, dependent, loan amount, tenure, co-applicant, credit history, property location, approved. These 13 were the initial ones. Then what happened? Total income log, EMI log, balance income log, right? So these comes into play. Now, what am I going to do? I'm going to drop certain of them. Why? Because though we see that, can create may or may not be coming into play. And not only that, now I am using the log values, right? So applicant income, I have applicant log, right? Co-applicant income, again, a log, loan amount, right? Sorry, this co-applicant doesn't have a log, but we created the total using the applicant and co-applicant. So these two can be dropped. Loan amount, we have it in log. Tenure and the comes with the total income and tenure will be in the EMI. So these two can be removed. EMI is in log, balance income is in log. So these features can be dropped, right? Again, similarly, loan ID adds no value for predicting the whether the customer is going to get the loan or not. So we can drop that. So finally, what happens in the loan data, which I will be sharing with the ML algorithm, are gender, married, self-employed, education, dependents, credit history, property location. Approved being your target variable, then total income, EMI and balance income logs, right? So these are the ones which will be used for building given as the input to the ML model. This is how the head looks like. Now comes the model building part. In the model building part, what am I going to do? The first step, I drop the variable, this target variable, right? Create the X wherein dropping the target variable. Now, Y is considered as the is stored for the stores the target variables. Columns, we have this set of columns, right? And then here we see that there are some dummies available, right? Those dummies needs to be converted. Naito, it will not be, dummies or null values. That then the some of the models will not work. So we check that, okay, whether there are null values, and then we replace them with either the median mode method, imputation method, or zeros as required, so that there are no dummies or no null spaces available in any of this different mm, uh, in the any of these features. Okay. So coming then, we have cleared the data, we have split the data. We'll split the target and the variables, right? The independent variables. Now what do we do? We have to scale the data because we are using regression in the following when we are building the models. So we scale. We are using the min-max scaler here. Okay, in this particular notebook, we are using the min-max scaler. X train is scaled and Y X test is scaled. Right. So now, after scaling this, what we are doing, we are feeding it into the logistic regression. Logistic regression, yes, we saw in the last class how we build from sklearn linear model, import logistic regressions, right? And import also the performance metrics, which we are using our accuracy scores. Train it, fit it, get the model coefficients, right? Right? Predict it, and then see the accuracy. We see that the accuracy is around 0.685 or say 0.69, 69%. It varies anywhere between that to 70. So we have seen that 74 being the maximum value obtained, accuracy obtained. Okay. Now, here we have using the logistic regression to list the feature the logistic regression coefficients. Okay. Absolute coefficients is what we are checking into for all the different features. Now, that being said of logistic regression, we come to the meat of the thing of building other ML algorithms such as decision tree, naive Bayes, random forest, SVM, and XGBoost. Okay. So here, what is it I require? We require PyDot. So I'm pip installing the PyDot first. Okay. Here, the different things required. One is train test split. Okay. Decision tree classifier. sklearn tree has this decision tree classifier. Okay. sklearn metrics, accuracy score, classification report, and confusion matrix. Matplotlib and Seaborn. We have already imported this. We need not repeat it here, but for reference, it's been mentioned here. Now, why the target variable is Y, the approved or not approved, and the rest of them are your rest of the features are given as the input. Now, train test split, what we do? X train, X test, Y train, Y test. So, train test split. What am I doing? X and Y is created. I'm giving the size. Here, 20% of the data is taken as the test size. The rest has the train data set. Random state 42 for reproducibility. Stratify, we say yes. Build and train the decision tree. Gini index is used. You can use entropy. You can try playing around with these values, the hyperparameters. Maximum depth is set at 4. Random state. What we do we here? Here training of the model is done. dt underscore model dot fit x train y train. So here the decision tree classifier is trained. Okay. For the hyperparameters of Gini and maximum depth of 4. Evaluate, then the prediction. How do we evaluate? We have already got this predictions. Y predict is equal to dt underscore. Same as how we have did it in the logistic regression side. Most of the models are already pre-built. All we have to do is pull it from the library, train it, use predict, and list the evaluation scores. Y predict is equal to dt model predict x test accuracy classification report confusion matrix. All this is printed. We see for the decision tree we get an accuracy of say around 82%. In the train accuracy it is 83, whereas in test it is around 82% classification. So this is how you get your report and your confusion matrix. Right? Feature importance is nothing but listing the different features to see how much of importance is obtained. This is based on your Gini value, right? The entropy value or the Gini value. You can find the feature importance. There are times wherein, you use this feature importance to say, okay, the top 50% of the features I consider and see how my model works. This is part of feature selection part. Next comes the random forest. Similar to the decision tree, RF model, random forest classifier. You have there we had the type of impurity calculation, whether it is Gini or entropy. Here it is n estimators. We set it as 100, maximum depth as 5. Train the model, predict the model. Predict. So we see again for my random forest, it is similar of around 82%. Right? Next comes the naive Bayes. sklearn naive Bayes import Gaussian NB. NB model Gaussian NB. NB model fit X train, Y train. No hyperparameters here. We just directly fitting the data, training the data and evaluating it. We see that for naive Bayes, it's around 65%. Not a great score. Okay. That next comes SVM. We import SVC as a kernel used as linear, probability true, train it and get the evaluation performance metrics. So basically, as you see, all these different models in Python are already present. We just have to pull them, set the hyperparameters as required, train them and predict. Okay. So this being SVM and the last being XGBoost. Okay. XGBoost import from XGB as a GB classifier, train it and run after training, you run the evaluation prediction. You see that the accuracy is around 78%. Now, what do? I now create an array wherein I score the different values of all the models and then print it. So this will be your summary. SVM gets the highest, 86%. Decision tree 82, random forest 82, XGBoost 78, logistic and naive Bayes has around 65. Okay. The other last concept is the k-fold. You all know what validation is, right? So here we are using cross validation to check in the different iterations what the values are. In the logistic regression, we see that it is possible to get it till 73%. So this ends the various classification models. Like I said, please feel free to run the notebook. Those are shared. Run the notebook. Right? Probably I'll just put it here as reference. As reference. Okay. Here we go. The notebook and the 3 different data sets. These are here for your references. You can also download it from the e-portal, right? And run the notebooks. See whether you face any challenges. Add different kinds of, try changing the hyperparameters of the ML models, right? And play around with those hyperparameters. See whether there is variations in the accuracies. I'll keep this session live. I'll keep the session live for some more time to see if any of you join, or and then we'll end the session. I will be uploading the second lab worksheet today or tomorrow. You will have time of 10 days to finish your lab sheets. Okay, lab worksheets. See to it that you are working those lab worksheets in the virtual environment only, the virtual lab provided. If not, there will be marks cut for it. Like I said, once when you are done with running your notebook, see to it that you stop the instance. That you stop the instance. Just like while starting, it takes a couple of seconds. Here, similarly, while shutting down, it takes a minute or two. I am loading the notebook and the data set here in the e-learning portal. Please feel free to download them, run them, and in case of any queries, feel free to reach out. PPTs, the notebook, and the data set. So there we are. All the material is uploaded. Work on them. Feel free to reach out anytime. I'm keeping the session live for another 10 to 15 minutes. In case if anyone of you joins, we can have a quick discussion. I shall stop the session here. All the best for your second lab sheet. Thank you all.